So for this segment, we're going to discuss how does a buffer work. And so for this, let's start with our previous setup where we had a concentration of our weak acid, acetic acid, and a concentration of its conjugate base, acetate. So for example, in the very beginning, we talked about what happens if we add into this. So here we've got the solution. And in solution, what the reaction looks like, if you will, is acetic acid dissociating in water. This is where we always go to. This is our go-to for our conjugate acid base equation. And now I'm going to add into this HCl. Okay. And we might add 1 ml of 1 molar again HCl. So again, we know this to be a strong acid. And an acid looks to react with what? A base. It wants to get rid of its hydrogen. So it's going to react with a base. So when we come up here and we look, we have acetic acid and its conjugate base. So this strong acid is looking for a base to react with. It's going to react with the acetate. So the first question that I taught y'all to ask after you figure out what you have and you say, okay, I've got a buffer, so have a buffer, so we know that. That's step one. We have a buffer solution. Step two is there a reaction when we add HCl? And yes, there is, because we've got HCl that will react with the base. So HCl plus the base, which is my acetate. And will this be straight arrow or double arrow? Exactly. It's going to be a straight arrow because we know this is a strong acid. The second that either of these, the acid or the base, is strong, you're going to have a double arrow. They're both strong, single arrow. Sorry about that. The second that you have a strong acid or a strong base, straight arrow. If both are strong acid, strong base, still straight arrow. If both of them are weak, we probably don't have a reaction. We have an equilibrium. So here we've got HCl. We see that what happens is we've got our acetic acid and we've got our chloride minus left. And so we do have a reaction. So here what happens is that HCl is going to be consumed by the acetate. Conversely, if we add a strong base, so now if we add, say, 1 ml of 1 molar sodium hydroxide to this solution above, is a reaction going to take place? Well, we have a strong base. What does it look for to react with? That's right, an acid. So we've got sodium hydroxide wanting to react with an acid, and we've got acetic acid here. Will this be straight arrow? Absolutely, because we have a strong base. And then, of course, we're going to see the transfer of this, and we'll have sodium acetate plus water. So there's my reaction. And again, this acetic acid is there to get rid of the sodium hydroxide. So the first thing that we do is, what do we have? We've got a buffer here. The second thing we do is a reaction when we add something else? So we've got to figure that out. What does the reaction look like? And then we're going to take this a little further. So if we continue this, now we've got numbers, and we have 0.1 mole of a strong acid reacting. So in this case, I'm going to start again with my reaction. So this is step 2. Do we have a reaction? We've already determined yes. So we've got our strong acid and our conjugate base reacting. And we're going to see what happens. So we've got initially, so this is initial number of moles that we're starting with, and the acetate that we started with, if you go back to that first problem from the in-class, I believe this is your second in-class problem on your sheet. This is, and so we're using the previous information, so we have 0.5 moles of this to start with in 1 liter, and here we have 0.1 mole of this strong acid, And then we have the acetic acid here, which is 0. Actually, it's not 0, is it? We started with 1 molar or 1 mole per liter. Now notice this chart needs to be in moles. So now we look and say, here's our third part. Do we have a limiting reactant situation? Yes, we do, because what you'll notice is we have moles of both my base and acid. And so because we have starting amounts of both, we need to figure out which one is limiting reactant. Well, it makes it simple because they're all 1 to 1. So we can see that our limiting reactant is HCl. So for every 0.1 moles of HCl that are consumed, 0.1 moles of acetate are consumed, and 0.1 mole of acetic acid and 0.1 mole of chloride are produced. Because for every 1 mole, according to this equation, for every 1 mole of HCl that's consumed, 1 mole of acetate's consumed, and so forth. So that tells me the change now in moles. And then my last step is to figure out what do we now have in the flask at the end. We might change that instead of final. I'm going to change that. Here's what we have in the flask at the end. Now notice this is in moles. So we have 0.4. We have 0 of the HCl and 1.10 of the acetate and 0.1 of the chloride. So notice, most importantly, is that did the buffer do its job? Its job is to get rid of any effect that the HCl or the strong acid would have. And you can see there's none left, so it cannot affect the solution. Now the next part of this question, I believe, asks you to find out what is the pH and should it be close to the original. Now our original pH you should have already determined. And so that original pH, when you determined it from your numbers, should have been, flipping through, 4.31, I believe, was that original. And now in this problem, you've got your 0 here. And then the next part of this, in order to solve the pH, is to ask, what kind of solution do we now have? And there are a couple options. One option is a buffer. Another option is we have just a plain old Ka, which means we have a weak acid in water. And another option is we could have a Kb, which means we have a weak base in water. So we got to figure out what's left over in order to figure this out. So if we come back up here, and we'll go blue, we got to figure this out. So what kind of solution? We have acetate and acetic acid. What are those? That's right, we have a weak acid and its conjugate base, or a weak base and its conjugate acid. So what kind of solution do we have? That's right, we have a buffer. So that means in order to find the pH, if we have a buffer, we can go straight to the Henderson-Hasselbalch equation. Again, I want you to do this for the class session that we will have, and that way you'll be ready. So work through that problem and finish that out and find the pH. Similarly, if we add here, keep moving forward, what if we have 0.1 mole of a strong base react with that same above solution? So now I'm going to go to our notebook. So again, let's say that we have our original solution. Like so. And now we're adding our hydroxide in there. So we've got a strong base. And I think it said 0.1 mole of that hydroxide. What's the first question you should ask after you have this buffer? Exactly. Does it react? So we've got our question. Does a reaction occur? Well, we've got a strong base and it's looking for an acid to react with, and lo and behold, we have our hydroxide, and it's going to react with the acid in my conjugate acid-base pair, so it's going to react with my acetic acid. Do I have a straight arrow? Correct, I do, because I have a strong base. And then on the other side, I end up with water. and acetate. So because I have a reaction, I've got to then ask, what do we have in the flask? So we've got hydroxide that's 0.1 mole. So these are our initial moles in the flask. We have acetic acid that we started with 1 mole, and we have acetate that's 0.5. We have water there. We're not going to worry a whole lot about it right now. And then we've got change in moles. And so we have to look at this and say, okay, do we have a limiting reactant problem? And lo and behold, we do, because we've got two different reactants with starting amounts. And so notice it's 1-to-1 again. So this is pretty straightforward. So we know for every 0.1 mole of hydroxide that's consumed, there's 0.1 of acetate consumed, and there's 0.1 of the or I should say minus 0.1 of the acetic acid consumed, and then we add 0.1 of the acetate produced. And again, we could do this with water, but ultimately when we're at the end and we're looking at pH, we're going to notice it doesn't affect it at this point. So we have 0, 0.9, and then we have 0.6. And then that next question that we were told to ask is, what kind of solution do we have? And we had 3 choices, and so I want you to look at this and tell me, what kind of solution do we have? Look at what's in your flask. You have acetic acid left over, and you have acetate left over. So what kind of solution is it? Perfect. It is a buffer solution. And so that means you can go straight to the Henderson-Hasselbalch, and you can calculate the pH of that solution. We're going to hold there for a second, and I'm going to ask you a question. Should the pH of this solution with this small addition of a hydroxide be significantly different from the original solution, the original buffer solution? It shouldn't, because it should maintain the pH, so your numbers should be fairly close. So I'm going to let you work that on your own and bring that into our Zoom session for class.